Any thoughts? All right, so now what we're doing is deterministic finite automatas. And, actually at the end of the last slide there were a couple other models, but let's skip those. We've done enough models. All right, so now let's do DFAs. This is one of the main topics of this course. And what is it? It's a Turing machine with no memory, right? No tape. It's just the Pooh Bear guy. So if we don't have memory, before, remember, we had the input on the tape. But now we don't have a tape. We don't have a memory tape. So the input's going to arrive to us in a stream. You'll get the first character, and then you get the next character, and you get the next character. And you can never reread it. Once it's come, it's come. So think about yourself as a Coke machine, right? You're in some state, and the user puts a quarter in, now you're in a different state. The user pushes this button, now you're in a different state. You can't go back and say, excuse me, user, did you put a quarter in before? Right? So here is, you're running this program, and the user is telling you to jump or go backwards or something, and as you go, you see more of the input. Right? A calculator is effectively a deterministic finite automata. It's in some state, and the user pushes buttons, which moves it to a different state. In fact, one of the examples we give is we'll give a DFA for building a calculator. Maybe jobs are coming, and you're processing them, or you're moving along a string, or you're moving along and you're trying to process it, right? So, and what is it? We're going to see later what is a language. A language is a computational problem where the output is yes or no. So for some strings we say yes, some strings we say no, right? And as you're reading this string, you have to think, what do I have to remember about what I've seen so far so that I can know the answer in the end, right? Because anything you need to remember, you have to store in your states. And just as before, we're going to store our states by writing things on Pooh Bear's blackboard, which will mean we're in the state which knows these facts. All right? And we're going to have a loop invariant, which that's the loop invariant. It's going to tell me what do I remember I've seen so far will be the loop invariant. And one of the rules is that it's a finite automata, so you can, at compile time, when you build the DFA, you can give it as many states as you want. You can give it as much blackboard space here as you want that you can write on, but once you've made the machine, then a bigger input's going to come, and you can't change the size of the memory, right? Everybody? So there are different ways we're going to view this same object, right, this DFA. We can think about it as a code with a simple loop. We can think about it as, and what's happening there, right? Each iteration, you're going to read in the next character. So you can't read that code, but one of the lines is, get me the next character, right? And then when you see this character, then the program is going to have a certain amount of memory, right? And that memory is bounded, but it's remembering something. And then when it reads the next character, it changes what it remembers, right? It updates its local memory as it goes around. And the loop invariant will say, what is it that I'm remembering? At the top of the loop, I'm remembering this about what I've seen so far. I get the next character, I update what I know, then the loop invariant is I remember something about what I've seen so far. Right? Does that make sense? The DFA focuses on states. So each node of the graph, just like we've seen before, is a state, and there'll be transitions between the states. So here, if I'm in this state and I read a 0, then I come down here. If I'm in this state and I read a 1, I go over there. Right? And so we can think of the computation as a path, as it's following a particular path through this DFA. Then we're going to talk about non-deterministic finite automata. And why do we talk about those? Partly just to torture you. All right? It's sort of a concept. Non-determinism is a concept that comes up in the theory of computation a number of times, so having one little example of non-determinism won't hurt you. It's also easier to build a machine that's non-deterministic, and then we're going to have a way of compiling. If you give me a non-deterministic one, there's an algorithm for compiling it into a deterministic one. And so that's one of the things we're going to do. Regular expressions are, if you're doing something in Unix, you certainly write regular expressions, and it's a useful tool to understand. And then the formal definition of a regular expression just allows clinging stars and unions and concatenations. I don't know, because those are easier to implement. So the harder ones are complement and intersection are harder. And so that's just another model of computation that's interesting. And what we're going to prove is that the set of languages that can be expressed by these machines is the same. So that's saying if an extended regular can do it, then there's a way of compiling it into just a regular expression. And there's a way of compiling that into a non-deterministic finite automata. And there's a way of compiling that into a deterministic finite automata, right? And so in some ways, what is the next part of this course is defining all of these models, learning how to build algorithms in those models, and then learning how to compile from one to the other, right? And then we're going to do one last fun thing, which is we're going to look at various computational problems and prove that they can't be done by this, right? And as a heads up, this is the set of all strings that have some number of zeros followed by the same number of ones, right? And so if this is the input, you're supposed to stop and say yes. And if the input has an extra 1, then you're supposed to stop and say no, right? But if you have finite memory, when you're going through the zeros, you can't count all the zeros, right? So we're going to consider that. Does it make sense? Yeah?
The non-deterministic finite automata, what does it mean to get help from the theory of God?
We haven't gotten there yet. Yeah, hold that question for a few days. This is a summary of the next couple of weeks. All right? So I think I might have told you this on the very first day. I always was thinking this course was really too hard for a second year place because I got notes from some people who were teaching it, and we prove all of these great things, right? And the proofs aren't that hard, but they're kind of hard for you guys, right? And so then I was talking to Zbigniew, who was the guy who's pushing that we need this course, and it turns out he doesn't do any of these proofs. All right? So now last term I removed a number of the proofs, and maybe this term, because we're now weeks behind, we might, right? Maybe we'll remove some of the other proofs. We'll see, right? But at least you should understand how do I. Right? The advantage of the one kind of proof is how do I compile from one to another? And the advantage of me teaching you that is that it's very mechanical. I give you one and you compile it into the other. And the advantage of that kind of question is you can memorize how to do it, and it's easy to put it on the test for you to get, right? If I ask you to prove something, you'll die, right? So we're going to work on, that kind of things, right? And I'd also love to have some extra time at the end of the course so we can do machine learning. So let's think about, as we go through here, how many of these proofs, what level you need to know all these proofs, all right? All right. What does this say? I don't know. Right, so this is kind of what I was saying about constant time versus fixed time again, right? At constant time, at compile time, the user gets to decide how many lines of code they want and how many states they want, right? They can decide how many variables they want, and every variable needs a fixed range, right? And then those are fixed. We've seen all this kind of stuff before. People remember this? This is just a reminder in a regular language, right? Given a regular language, remember I said all those machines can compute the same set of functions? They're called regular languages, right? So they can all compute regular languages. So this is just saying for every regular language, right, I can build a constant memory Java program that how much memory does it have? It has, say, K memory, or it has K states, or it has, right? And then as the input grows, the amount of memory doesn't change, right? This is what we mean by a constant amount of memory. Everybody remember, if we've done enough first order logic, you should know this. Everybody get this? Right? And so how are we going to do it? Right? This is on a test, I'm going to give you a language, and you are going to build maybe a little piece of code that does it. Or maybe you'll build a DFA for it or an NSA for it, right? And then the guy here complains, well, how much memory or how many states can you give it? You can give it as much memory and as much states as you want, right? But then it has to be fixed when the input comes, right? So back to this problem here, something that I've had 1 million students say to me, right? Can I compute whether it has this many zeros followed by this many ones, right? Yeah, there's a DFA that does that. It can count up to a constant and then count up to a constant, right? But once you give me the DFA, it has a fixed number of states. So if I make my input bigger, then you no longer can count, right? So that's why I keep playing with these differences. All right, so what are we doing? We're going to first think about